Hello, my name is Mārtiņš Zubkins and I'm a leading researcher at the Institute of Solid-State Physics, working at thin films laboratory. And today's lecture is about photochromic thin films, and I will focus on bilayer composition, yttrium oxide and molybdenum trioxide. This is the outline of my talk. In the beginning, I will introduce basics of photochromism. I will introduce yttrium oxide and molybdenum trioxide, and then I will explain the idea behind bilayer structures, why we decided to study them. Next will be experimental details. I'll show you how we produce the films. We use reactive magnetron sputtering. And then the main part is thin film characterization. I will show the structure and optical properties of these films, and of course the main part will be photochromic activity measurements. And to interpret and explain the results better, then we use chemical composition analyses. In the end, of course, I will give the main conclusions that will contain the information how the thickness and density of molybdenum trioxide thin films influence the photochromic results. Well, photochromism. The basic definition is that when we illuminate the material with some light, it changes its optical properties. And this effect should be reversible. So either one or another way, the material should recover to its initial state. Well, the light we use should be of energy enough to excite the material from one state to another so that the optical properties are changed. How we can modify photochromic properties? Well, either we can change the structure of material, adjust the composition. For example, if we talk about thin films, then we can modify morphology or preparation technique. And also we can use hybridization of material. What are the main properties we look at when we are studying photochromic thin films? Well, the first is the photochromic contrast. In general, we want to increase it, and the larger, the better. Then, of course, the photochromic change speed, or how fast a material reaches either dark state or how fast it bleaches back. Then also repeatability. We want that this photochromic contrast has low fatigue. And then also the material stability itself, because we don't want that material loses its properties over time. And in the end, we need to combine all these properties so that they are suitable for some desired application. Here are the main applications for photochromic thin films. Of course, I would say the success story for photochromic materials are glasses, which turn into the sunglasses when we go out in sunny day. Here we are more focused on smart window application. In this case, we need to make photochromic materials in larger scale. That's the first thing. And the idea is to reduce energy consumption. For example, at sunny summer day, we would like to reduce the heat transfer in our indoor so that we don't need to cool our buildings. So at sunny days it would darken, and in cloudy days it would stay in the clear state. Also, automotive industry is interesting. We could use these coatings for the windshields or roofs to increase the comfort and also the safety during driving. Also, photochromism found its usefulness in optical storage, also in security, and in sensors or indicators. And actually, that bilayer structure that I will talk in detail today actually has properties suitable for indicators. On the right side, you see overview of number of publications published year by year, and you see that the number increases. However, the total number of publications still isn't that much. And if we check how many of these papers are about inorganic photochromism, it's still the lower fraction. I made this brief history overview of photochromism, focusing on main discoveries in inorganic materials. But I couldn't skip, of course, some organic materials, because materials phenomena itself was discovered in organic compounds, and it was discovered in 1867 in tetrazine. Then in 1896, Goldstein reports some coloration of alkali halides under irradiation of high energy flux. Although this shouldn't be called photochromism, it's more related to the formation of defects in inorganic solid. Then first solid but still organic material was reported in 1899, and then crooks absorb violet tint in glass under sunlight in 1950 year, and first synthetic produced photochromic inorganic solid materials were studied and produced in 1930s and 1940s. And up to 1950, actually, this phenomena was called phototrophy, which this term actually isn't that suitable because it's more related to biological processes. So in 1950, the term photochromism was proposed, which is more suitable, from Greek words phos, light, and chroma, color. Well, I think really important discovery in 1964 in photochromism in silver halides, and based on this material, photochromic glasses later were produced. Then, relevant to our lecture today, photochromism molybdenum trioxide was discovered in 1966, a little bit later also in tungsten trioxide, which is an analog compound really similar to molybdenum trioxide. In 1980s, first hybridized photochromic materials were studied, and in 2011 in Norway, Mongstad discovered photochromism in oxygen containing yttrium hydride or yttrium oxide, which actually opened a new group of photochromic materials, because several of rare earth oxyhydrides exhibit this property. The basic principle of photochromism that material has two states, A and B. A is thermodynamically stable, B is metastable state, and we can reduce or excite material from A to B by illuminating the material by some light. And depending how the material recovers to its initial state, either just by thermal energy, then we call this effect T-type. If we need different light energy for material material illuminated to be able to recover, then it's P-type. And then if material darkens under illumination, it is positive effect. And if it works with sunlight, then we call heliochromic. However, if material bleaches under illumination, then it's negative photochromic effect. Here is presented the different type of compounds known organic compounds. This is not the focus of my lecture today, but in general, under illumination, the form or structure is changed in organic compounds. Either bonds are broken or new are formed, and the optical properties change. For inorganic compounds, there are transition metal oxides, tungsten trioxide, molybdenum trioxide, titanium dioxide, vanadium oxide, alkaline earth sulfides, titanates, metal halides, for example, silver halide doped with kappa, even heterojunctions and Schottky barriers. Rare earth doping is frequently used, and also rare earth oxyhydrates that I mentioned already. And then there is the third group, which is organic inorganic hybrids, usually photochromic organic compound molecules are placed into the inorganic matrix. About yttrium oxyhydride. Here on the left sided top graph, you see transmittance spectra of yttrium oxyhydride. You see it's quite transmittent. We can adjust the thickness of the film so that the transmittance spectra nicely match with our eye sensitivity spectrum. And in this case, before illumination, the film is around 80 to 70% transmittent, and then we illuminate it, and you see that transmittance spectrum gradually decreases, and that decrease is in whole spectrum. That's why this for yttrium oxyhydride is called color neutral effect, because no new absorption bands are formed, but all spectrum decreases. The problem is that the material absorbs quite a lot in blue part of the spectrum, giving its yellowish tint, which is kind of a problem at the moment. The structure yttrium forms phase cubic structure where oxygen is placed in the tetrahedral sites. Hydrogen can be both in tetrahedral, octahedral sites, or even in some interstitial sites. In this representation, in my presentation, hydrogen also is placed in tetrahedral site. At the bottom on the left side, you see the cycling, photochromic cycling. We illuminate the material 1 hour and then switch off the light. In this example, you see the contrast is around 30%. And also in this case, darkening rate is higher compared to bleaching rate, because after 1 hour of bleaching, the film hadn't reached its initial state in transmittance. Also, what we discovered that the photochromism for this compound can be observed far infrared region, up to even 5,000 nanometers. Well, what are the challenges? It seems from our experiments that darkening and bleaching rates are reversibly linked. What I mean by that is that if we can make the material with higher darkening rate, then the bleaching rate will be lower, but in principle, we would like to increase both of these rates. Then environmental stability still remains a concern. Then the origin of photochromic mechanism in this material is still not completely understood, and even the phase, either this material is completely homogeneous or it's several phases, it's still under study. And I already mentioned yellowish tint of it. About molybdenum trioxide. Actually, it's a very well-known chromic material. It exhibits electrochromic, gasochromic, and photochromic properties. In electrochromic device, which is basically battery-type structure, positive ions are injected into the molybdenum trioxide together with electrons, and then the reaction happens and molybdenum bronze is formed, which absorbs more in the visible light spectrum compared to molybdenum trioxide. And this increased absorption is explained by intervalence charge transfer between molybdenum 5+ and 6+, or also polar absorbance is considered. In gasochromic applications, we must have catalytic compound so that the gas is splitted, and then ions can intercalate into the molybdenum trioxide to reduce molybdenum again. In principle, if we split hydrogen, then again we are producing molybdenum bronze. And for photochromic, it's not that clear because it seems that we must have some water inside the molybdenum trioxide so that when the material is illuminated by UV light, electron and hole pairs are produced, and then this water can be split into the molybdenum trioxide, and again hydrogen can react then with molybdenum trioxide and form molybdenum bronze. At the bottom left side, there is a graph from one of the first papers about molybdenum trioxide photochromism, and after illumination, increased absorption was observed, and absorption bands, several of them. Well, molybdenum bronze actually is not easy to recover, and when hydrogen concentration is high enough, actually it's quite unstable and can decompose into the molybdenum dioxide and water, and in that case it cannot recover to its initial state. And also, when the films are quite stoichiometric, then molybdenum trioxide doesn't show photochromic activity. And this is important also for our lecture. About the idea of bilayer structure, well, Dmitry Moldarov, scientist from Sweden, discovered that actually when you eliminate yttrium oxide, especially in the first illumination, there is a release of hydrogen outside of yttrium oxide. So in principle, if we deposit molybdenum trioxide on top of it, then molybdenum trioxide can accept this hydrogen, and again, very well already discussed reaction can happen and molybdenum bronze can form. This is the idea. And in our study we thought let's study how, for example, thickness of molybdenum trioxide or density influences. The concept is not new. It's already shown in yttrium oxide tungsten trioxide bilayer structures. This is the system we use to produce samples. This is vacuum system equipped with magnetron sputtering, and you see there two magnetrons where the molybdenum target and yttrium target were placed. At the beginning, we produce yttrium dihydride. We sputtered yttrium target in argon plus hydrogen atmosphere to produce yttrium dihydride, to produce phase cubic structure of it. And this is very important because when we try to add also oxygen during deposition, well, it seems impossible to obtain right phase of material. So yttrium oxyhydride itself should be produced in 2 steps. First yttrium dihydride, and then we oxidize it, either just exposing the samples to air or introducing pure oxygen into the chamber. And then we can change the density of yttrium dihydride. Usually it is done by varying the deposition pressure, and in that way we can change how much material will uptake oxygen and what will be the final composition of the material. And at the second stage we sputter molybdenum in argon plus oxygen atmosphere, producing molybdenum trioxide. We did 2 sets of samples. Here I will show what we changed there. In all samples we kept plus minus optimized yttrium oxyhydride always the same. You see here it was around 780, 770 nanometer thick yttrium oxyhydride, and we changed the thickness of molybdenum trioxide on top of it. All other parameters were the same. During the second set deposition, we tried to keep molybdenum thickness the same, around 80-90 nanometers, but we changed the deposition pressure of it. And in general, magnetron sputtering, we changed the density of material by doing this. And here at the bottom left side, there is indirect proof that actually we changed the density. We measured the refractive index of single layer molybdenum trioxide deposit at different deposition pressures. We see that at lower deposition pressures, refracting index increases. That indicates that the material gets denser. Although we also observe little change also in composition of molybdenum trioxide. We believe that density plays more important role in photochromic properties in the end, because we see that the molybdenum itself, it's quite stoichiometric, even over stoichiometric, and you will see further in my lecture that our single layer molybdenum trioxide films aren't photochromic. That I already said when I introduced molybdenum trioxide, that stoichiometric molybdenum trioxide usually doesn't exhibit photochromic properties. This is X-ray diffract diagrams that we can use to study crystalline materials. Well, you see almost all of them are quite the same. This is because in our case molybdenum trioxide was amorphous, and in XRD you don't see nothing from amorphous materials. And these patterns just showing us that in all cases yttrium oxyhydride basically was the same. It has its cubic structure, only that the films are quite textured in the 1-0-0 direction, because we see really intense 2-0-0 peak for polycrystalline material. 1-1-1 should be more intense. And we recalculated also the crystalline size of yttrium oxyhydride. The crystalline size was between 12 and 20 nanometers. These are electron microscope surface images. We see the morphology of our samples. If we look at single layer yttrium oxyhydride, it's very well dense, grainy features, well packed. And at higher magnification, we even see that these grainy features consist of smaller ones, and the size is quite well matches with the size we got from XRD measurements. When we cover this material with molybdenum trioxide, we see that the surface gets more porous. We did some additional analysis segmentation using local adaptive thresholding, where we see visually that molybdenum trioxide morphology is less dense. We see these open voids and places in the surface of molybdenum trioxide. These are cross-section images. For single layer yttrium oxide, we see columnar structure growth, which is quite often observed for magnetron sputter thin films at room temperature. And then when for covered or bilayer structures, very well defined two-layer structure is observed. Optical properties. This is pretty much all the films are with the same transmittance, and they absorb around under 400 nanometers, and this is because of optical band gap, and we recalculated the optical band gap values, and for both films the values are pretty much the same, around 3 eV. And now about photochromic properties. On the left side you see spectra before illumination, the black curve for single yttrium oxide. But for bilayer structures, as I showed in previous slide, the curves are pretty much the same. And then we illuminate the films for a long time. I think it was around 12 hours. And we see for yttrium oxide the contrast was 30%. When we cover this material with molybdenum trioxide, the contrast increases at least to 50%. And actually, for thicker films, the contrast is larger. And the explanation is that the more molybdenum trioxide, the more molybdenum bronze can form. And even for this, you see on the left side, yellow dash curve, there is this valley at 700 nanometers, which is characteristic for molybdenum bronze absorption band in this red part of spectrum. Then, if we decrease the deposition pressure of molybdenum trioxide, now we should look at second graph, then the higher contrast is achieved for denser films. This is the red curve. And again, the explanation is the same. Since the thickness for all of molybdenum trioxide films was the same, but denser film means more material, so more molybdenum trioxide, more molybdenum bronze can form. And on the right side you see this clear difference. You see that molybdenum trioxide, after 20 hours of illumination, in this case, molybdenum trioxide didn't show any observable photochromism or darkening, and you see that bilayer structure had higher contrast compared to single layer yttrium oxide. So this is the overview of mechanism we believe is under this. So we illuminate the bilayer structure, hydrogen is released from yttrium oxide, it migrates into the molybdenum trioxide. In meantime, electron and hole pairs are formed in molybdenum trioxide, and the reaction happens that molybdenum bronze is formed, and we in principle should see the partial reduction of molybdenum in molybdenum oxide layer. This is photochromic cycling. So we illuminate the films for 1 hour and let them to recover for 1 hour. Several things I want to mention here. First, you see that during bleaching, the films didn't recover, or actually stop recovering. There you see these plateaus at the end of second hour, and this is because molybdenum bronze doesn't recover, or molybdenum oxide doesn't recover back, and all the bleaching happens into the yttrium oxide hydride film. And the more we illuminate the films, the less the films can recover. And there's again clear correlation. The more or thicker molybdenum film on top of yttrium oxide hydride, the faster is the darkening, except the more you see this yellow curve for the thickest molybdenum trioxide. In the beginning we see that actually it darkens slower, and there is a clear explanation for this, because when we deposit thicker molybdenum trioxide, it actually absorbs quite a lot of effective UV light that can trigger photochromism in yttrium oxide hydride, and most probably also hydrogen release. So we must illuminate longer to form molybdenum bronze, and you can see in subsequent cycling this yellow curve starts to catch up, and after prolonged illumination it will drop the most, and this film will have the highest contrast in the end. On the right side you see the cycling for different densities of molybdenum trioxide. Here also in the beginning more porous films actually darkens faster, and this is also understandable because it's for hydrogen easier to penetrate in molybdenum trioxide if the films are more porous. But in the end, again, after prolonged illumination, denser films will exhibit higher absorption. And this is the evidence for molybdenum bronze formation. You see on the top two rows of XPS spectrum. XPS tells us about chemical state of material. And we see that in the molybdenum trioxide case, the spectra do not change after illumination, which means no changes happen. And also we see that for molybdenum signal, only molybdenum 6+ is absorbed, so also telling us that the films are stoichiometric. Although for bilayer structures, even before illumination we see some molybdenum 5+, and after illumination clear reduction of molybdenum from 6+ to 5+. And there is also difference in oxygen signal if we compare to single molybdenum trioxide films, that OH signal has a larger contribution in oxygen signal compared to single molybdenum trioxide films. Then we did the experiment. If actually hydrogen is released mainly during first illumination, we decided to produce two films. Yttrium oxide hydride, again completely the same, but before covering it with molybdenum trioxide, one of them was illuminated for a long time, and we let the film to recover to its initial state, and only then we cover it with molybdenum trioxide. And this is the green curve in this graph. We see that after illumination we don't see any more large increasement in photochromic contrast. the violet curve is the usual case. So indeed, most of hydrogen is released in the first illuminations. And now about stability or chemical stability. For one sample that we produced, we sticker molybdenum trioxide. In that case, molybdenum trioxide was 500 nanometers thick. After a couple of days, we observed it darkens by itself in just ambient lighting conditions in the room. So we produce again 4 new samples. We kept 2 of them in the darkness for around 50 days and 2 in ambient conditions. And again, we did one with pre-illumination of yttrium oxide and 2 without. And we see that if we don't use this pre-illumination and we keep it in ambient lighting conditions, it darkens by itself quite much. This is dark blue curve. Although if we pre-illuminate the films and keep it in the dark, actually the transmittance doesn't change. So in principle, we can use this bilayer structure to be as an indicator was or was not there some illumination of the sample during time. And then we did also nuclear reaction analysis, the technique that can detect hydrogen, and we measure for this bilayer structure which darkens over time the hydrogen concentration, and we detect 10% atomic percent in it. If we compare to single molybdenum trioxide, it's under 1%. So at least one order difference, and clearly proving that hydrogen diffuses into the molybdenum trioxide. And these are the conclusions. Well, we observed enhanced photodarkening in bilayer structures compared to single layer yttrium oxide hydride. This is related to the hydrogen intercalation in yttrium oxide hydride forming molybdenum bronze. XPS proved partial reduction of molybdenum 6 plus to molybdenum 5 plus. If we make the molybdenum films thicker and denser, after longer illumination, we will get higher contrast. But the films do not recover to their initial states because it's hard to recover molybdenum bronze. This is one difference compared to yttrium oxide hydride with tungsten trioxide, because it is reported if we heat that bilayer structure, it can be recovered. We tried yttrium oxide hydride with molybdenum trioxide and we didn't succeed. We also showed gradual darkening over time without intentional illumination, and nuclear reaction analysis showed direct proof of hydrogen diffusion into the molybdenum trioxide when it is in bilayer structure. So these are all the conclusions, and if you are more interested about these results, you can read our recent paper in Solar Energy Material Solar Cells that was published in 2025. So thank you for listening to this lecture.